Okay. So yeah, good evening everyone. Welcome to this live session for applied linear algebra. Um, and we are in the first live session. So I hope you all have access to the first week's contents in the NPTEL course web page. And so the agenda for today is to discuss some sample questions related to the contents of week 1 of the course. So I've prepared some questions myself, and pardon me for my bad handwriting. I hope it is readable. If not, let me know. And before I begin, let me give a quick introduction about myself. So my name is Avik Mukhopadhyay, and I'm a PhD research scholar at the Department of Electrical Engineering at IIT Madras. So I'm one of the TAs for this course. So every week on every Friday we'll have these live sessions from 6 to 8 p.m. Okay. So yeah, someone wants to join, I guess. Okay. Okay. So let's get started. And if you recall your week 1 contents, we were mainly introduced to the fundamental topics of linear algebra, the fundamental tools of linear algebra, namely vectors, matrices, and the certain aspects related to them. Um, Firstly, we saw what is the concept of a norm of vector, and then we studied certain inequalities associated with the norm, namely the Cauchy-Schwarz inequality. Then we also saw the linear independence and dependence of vectors, and we also explored matrices and looked at several matrix operations like addition, multiplication, and so on. Also, we were introduced to the idea of rank of a matrix, how to find the rank of a matrix, and also we saw briefly about the Gaussian elimination process, how to perform the row operations or row reductions, how to convert a matrix into its row echelon form, and so on. And also like the inner products were covered, and when are two vectors orthogonal, and so on. We studied these things. And also we, as this course is pretty much application oriented, a professor had given you one example of this correlation or this inner product in the area of radar, right? To detect if a aircraft is approaching or not, if an object is present or not. How can we use this correlation and compare with a threshold value, and accordingly decide whether the object is present or absent. So keeping these concepts in mind, let us begin today's session, and please feel free to interrupt me if you have any queries or anything if it's not clear. Okay, so this is applied linear algebra. Actually it's a big name, I'm just writing the first three words, and we are in, it's actually session 1, but the contents are from week 1. Okay, so this is the first question for today. mm, I'll let you go through the question, read it yourself everyone, and then we'll start how to approach solving this. Okay, just let me check if Okay. Yeah. Okay, so in this question, you are given two vectors, vector u and vector v. They're four-dimensional complex vectors. Okay, and the notation, I'll stick to this notation. I'll try to stick to this notation with a bar on top of the literal to denote that it's a vector, as was used by Professor Jagannatham. So these are two complex vectors. As the entries are complex numbers, you can see. So this small I denotes iota, which you are familiar with, is the square root of -1, and you have to compute the norms of these two vectors separately, and then you also have to compute the inner products between these two vectors. Okay. um, so you have to compare the inner product of u and v, and vice versa in the reverse order, v and u, and you have to verify that the Cauchy-Schwarz inequality, which we have seen in the lectures, is indeed satisfied, and also later on we'll have to verify the triangle inequality. Okay. If you are not familiar with the triangle inequality, don't worry, we'll see. Okay, so I hope the question is clear to you. These things, I think most of you would be familiar with all these things, but anyways, we'll go through them in details. Okay. Okay, so there are a lot of people joining. Okay. So here I'll write down the two vectors which are given. Okay. So the first vector is a 4 cross 1 vector with these entries, and the second vector is the vector v, which is also a 4 cross 1 vector with the elements 2 plus I, 1, 3I, and -1. Okay. So first we have to compute their individual norms, the norm of vector u and the norm of vector v. So yeah, if anyone wants to volunteer, how do we calculate the norm? Feel free to um, unmute and respond. Okay.
Uh, can I?
Yeah, yeah, sure, sure, sure.
So it is first will be under root 2 square plus 1 minus I whole square plus I square plus 9.
Correct,
That is 3 square.
correct, correct.
Yeah.
So exactly, this is how we find the norm. And just to be extra cautious, it's just not simply the square in this case, but the magnitude square, because we are dealing with complex vectors. Okay, because if you square small I, you'll end up with -1, right? But here you have to take the absolute value or the magnitude of I and then square. This is the general case of complex numbers. Okay, so it will be, the first element is 2. I'm computing the norm of vector u. So it's the magnitude of this first entry squared, magnitude squared, plus what is the second element? 1 minus I. So magnitude of 1 minus I squared, and so on. Okay, I'll just okay. And similarly, magnitude of I squared plus magnitude of 3 square. Okay. Okay, now what do we have here? So the first term equates to 4 because it's the mod square of 2 is simply 4. And what about the second term? It's the magnitude square of this complex number. It is a complex number, 1 minus I. You know how to find the magnitude of a complex number, right? So in general, I mean aside, if you have a complex number z denoted by x plus iy, so this belongs to the set of complex numbers denoted by this bold c. So the magnitude of z is given by square root of the real part squared, which is the x, and the square of the imaginary part, which is the square of y. Okay, I think most of you would be familiar with this. So we will take the magnitude square of this second term, which is 1 minus I. Okay, so it will be square root 2 the square, which is same as 2. Okay, I'm directly writing, or maybe I should just for completeness I'll write it like this: real part square plus imaginary part square. Okay, and for the third term, so its magnitude is simply 1 squared. Okay, so it's 1, and the last term is 9. Okay, I hope so far so good. So this results in 4 plus 2 plus 1 plus 9, which is I think 16, if I have not made any mistake. So what is the final answer? This is equal to 4. We are excluding the minus sign here, because on taking square roots there are two possibilities. It can be either plus or minus 4, but the negative numbers are eliminated because we are dealing with norm, and norm, as you know, actually in layman terms is the length of a vector. So I mean negative length doesn't make any sense here. So norm cannot be negative. It is surely non-negative. The least it can be is 0 or positive. Okay, so we'll stick to plus 4. Similarly, you can find the norm for v. Okay, this is the notation. Okay, so what is v? V is another complex vector with these entries: 2 plus I, 1, 3i, and minus 1. So again, using this formula of norm, we will just compute its norm. Okay, so it's the square root of mod of 2 plus I the square. Okay, lot of people are joining, which is good. Okay, yeah, and the second term is mod 1 squared plus mod 3i squared plus mod minus 1 squared. Okay, it's just written down on the same logic, and if you equate it, first term again you have to take the square of the real and imaginary part separately. So this is like this, and the rest of the things are straightforward. So again, if you evaluate this, it should be 5 plus 1 plus 9 plus 1, which is again square root of 16, and which is again plus 4. Again, we are not considering the negative value because norm is non-negative. Okay, so we are done with the first part of the question, which asked us to find the individual norms, right? Now we have to find the inner products of these two vectors, both in both directions. Okay, so let's first compute inner product of u and v, okay, in this sequence. And if you recall your lecture notes, the definition is, since we are dealing with the general, more general complex vectors, so the formula is u Hermitian times v. Okay, you take the Hermitian of the first vector and multiply with the second vector as it is. And what is Hermitian? This capital H, it is the transpose conjugate. You take the complex conjugate and as well as the transpose of the vector. Okay, so if you so what is u Hermitian in this case? If u is this, can someone quickly tell me what is u Hermitian? U is written on the top. What happens if we take the transpose and the conjugate of this?
So 2, 1 plus I
Correct.
minus I and 3.
Minus I and 3. Yeah, and it becomes a row vector. Now it's a column vector. On taking the transpose, it becomes a 1 cross 4 vector or a row vector, right? So, and exactly the elements are what you just said, absolutely right. So it becomes 2. The second element now becomes, okay, 2 remains 2 because it's a real number, right? Taking the complex conjugate of 2 doesn't make any change, right? It still remains the same. So on taking the complex conjugate of 1 minus I, it becomes 1 plus I. That's what I have written. Similarly, plus I becomes minus I and 3 remains 3. And the vector became now a row vector. Initially it was a column vector because we are taking the transpose as well. And v is as it is, okay, like this, 3i and minus 1. Okay, now what we do, okay, this is a 1 cross 4 vector, this is a 4 cross 1 vector. Okay, the multiplication makes sense. In the more general case of matrix multiplication, we know that the if we have a product like A times B, where A and B are two matrices, the number of columns of A should be equal to the number of rows of B for the product AB to be defined. So in this case, these are vectors which are special cases of matrices, right? This is just a single row or a single column. So here also you see the number of columns of the first vector, which is this 4, is the same as the number of rows of this second vector, which is 4. So the dimension matches, so we can take the product, the pointwise product or the inner product. So it's just, you know, pointwise multiplication and addition, as you know. So now what is the result of this? We have to just take the pointwise product, so which is 2 times, this is the first element here, this is the first element here, so multiply them together. Okay, so 2 times 2 plus I. Now this is the second element here, this is the second element here, multiply them together. Okay, and we'll keep adding the terms, so plus 1 plus I into 1. Similarly, the multiply the third elements together and add them up, plus minus I into 3i, and lastly 3 into minus 1, sorry. Okay, so this is if you calculate it, it becomes 5 plus 3i. Okay, see the last two terms will get cancelled out because minus I into 3i becomes plus 3 and the last term is minus 3, they get cancelled out. So only you have to add the first two terms, which equal to 5 plus 3i. So you see the inner product of these two complex vectors results in a value which is a scalar value, but in this case it's a complex number, which makes sense. You are taking the inner product of two complex vectors with complex entries, so you get a complex valued answer. Okay, fine. Now what we will do is, in the next part, you see you have been asked to verify the Cauchy-Schwarz inequality. So in the Cauchy-Schwarz inequality, we saw, right, the inner product is upper bounded by the product of the norms of the individual vector. So in this case, the absolute value of this inner product of u and v is less than or equals to the product of norm of v and norm of u, right? So that's the statement of the Cauchy-Schwarz inequality. So in order to check that, first let us find the magnitude or the absolute value of this inner product. So I'll just take the magnitude of this. Okay, so this is the magnitude of 5 plus 3i, which is again in red color as I have written on above. How to find the magnitude of a complex number? You take the squares of the real and imaginary part and take the square root. So this becomes square root of 5 square plus 3 squared, so it is square root of 34, and approximately it is like some 5.83. Okay, I'll move to the next page. And now to verify the Cauchy-Schwarz inequality, what we will do is um, on the right hand side of the inequality, you have the norms multiplied together, right? So in this case, what is the product of the two norms? Norm of u times norm of v, correct? And we have already computed them. Both have value 4. So this is 4 times 4, which is 16, correct? So this indeed satisfies the Cauchy-Schwarz inequality, because you see on the left hand side we have the magnitude of the inner product, which is 5.83, and on the right hand side we have the product of the two norms, which is 16. So 5.83 is definitely less than 16. So clearly this is being satisfied, correct? So the Cauchy-Schwarz inequality holds, it's satisfied. And similarly, we are also asked to find the inner product in the reverse direction, that is the inner product of v and u. So this will be again using the same process. This will be v Hermitian times u. Okay, and again we will take the transpose complex conjugate of v. So v is this vector, so it will become a row vector. So this will become v Hermitian is equal to 2 minus I plus 1 minus 3i minus 1, and u is as it is. So this is 2 1 minus I and 3. Okay, again this product makes sense because this is 1 cross 4, this is 4 cross 1. Okay, so again you take the pointwise multiplication and add them up, so you'll get 2 times 2 minus I plus 1 times 1 minus I, which is 1 minus I, plus 1 plus minus 3 times minus 3i times I, so that gives you 3, and the last term would be minus 1 times 3, which is minus 3. And here this equals to 5 minus 3i. Okay, so initially when we took the inner product of u and v, we found it is equal to 5 plus 3i, and here when we took the inner product in the reverse direction, that is the inner product of v and u, the result turns out to be 5 minus 3i. So clearly they are not matching. Okay, but yeah, so clearly the inner products are not matching, and so you can conclude that this general inner product of complex vectors is not commutative, right? So you simply swap their orders and you can get a different value. So this is the, I mean, they are not commutative. If the two values would have been matching, then you can argue that it's actually the same. For real vectors, actually it's the same, but here you are taking the complex conjugate, right? So and the uh, correct observation is that these two results will be the complex conjugate of each other. So you see the previous answer we got 5 plus 3i. When we change the order, we got 5 minus 3i, which is the complex conjugate of the previous result. And it makes sense, right? Because in this case, like the we are dealing with complex vectors. So on the first case, we are doing the transpose and complex conjugate of one of the vectors, let's say the vector u. But in the other case, we are doing the complex conjugate and the transpose of the other vector. So that's why it's changing the sign. So the results are not matching in the two cases, and indeed they will be the complex conjugate of each other. So as a side observation, you can note that in general for complex vectors, uv inner product is not necessarily vu inner product. So which means inner product of complex vectors is not necessarily commutative. Okay, in fact, as I said, uv is actually is actually the complex conjugate of the inner product of v and u. So this star denotes complex conjugate. Okay, and in the case of real vectors, this conjugate has no function actually. So that's why for real vectors this is clearly commutative. Okay, you perform the inner product of u and v, or you perform the inner product of v and u, both are same. Okay, 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 good. So this is a small observation, and now you can also actually verify the Cauchy-Schwarz inequality in the reverse order as well. So we computed the inner product of v and u, and on taking its magnitude we will again get square root of 34. Again it's 5.383 is the same, and on the right hand side of the inequality we will have the product of these two norms, which is again 4 times 4, which is 16, and again the Cauchy-Schwarz inequality is satisfied. So again in this case as well, yeah. please let me know if I make any calculation mistake or anything, if you spot any errors or if anything is not clear. um, okay, otherwise I'll assume that things are okay. Okay, now moving to the last part of this problem. So we are done with the Cauchy-Schwarz part. Now you are asked to verify the triangle inequality. Okay, this is something I think it's uh, not something not covered in the lectures, I guess, but it's pretty straightforward actually. I mean, the statement is essentially saying that the sum of two sides of a triangle is greater than the third side, greater than or equals to the third side. I mean, the equality is a special case where you have like parallel lines, so to speak. So the angle between two lines is either 180 degree or 0 degree. That's special case. So yeah, I mean, so basically the task is to prove that this norm is less than or equals to the sum of these two norms. Okay, this is the actual statement of the uh, triangle inequality. To prove this is the triangle inequality. Okay, let me admit. I should not actually use the term prove here because we are not proving the triangle inequality, but I mean to verify actually, because in the question the term verify has been used. You have to just check whether this inequality holds or not. Okay, so what this saying geometrically is, let's say these are two vectors. Okay, these are the sides of a triangle. So this is vector u, let's say this is vector v. I mean, it's a straight line, although it doesn't appear to be straight. And let me take another color. This is vector u plus v. Is the same old, those concept of resultant vector as we have studied in vector physics, right? So it's the same thing. So the length of this u plus v is less than or equals to the sum of the lengths of u and v, which is the same as saying that okay, sum of u and v should be greater than or equals to the third side, which is u plus v in this triangle. So it's easy to check actually. I'm not proving it. I think you can prove it. It's pretty simple. It's available online also. So due to restricted time we are not proving it, but to verify it, it's pretty simple actually. So I'll move to the next page. So what is u plus v? We have to add these two vectors. First vector is 2, 1 minus I and 3. Second vector is the vector v, which is 2 plus I, 1, 3I and minus 1. Can someone quickly tell me the result of this addition? Okay, I should admit, I think. Okay. So yeah. So what's the result of this addition? Anyone? It's just a review of the basics. Yeah, yeah. Go ahead.
4 plus I, 2 minus I, 4I and 2.
Correct. Absolutely right. So this is 4 plus I, 2 minus I, 4I and 2. So we are adding the elements together pointwise. So the first entry of vector u gets added to the first entry of vector v. Similarly, second entry of vector u gets added to the second entry of vector v, and so on. Okay, and it applies to the general case of matrices as well. You do, whenever you add two matrices together, you follow the same logic. You perform the pointwise addition. Okay, now you take the norm of this. You need the norm of this quantity, right, in order to verify triangle inequality. That's why it's written, that's why it's mentioned also, find the norm of u plus v in the question. Okay, so again, using the norm formula, mod square magnitude square of this, magnitude square of this, magnitude square of this, and lastly this. So this is, again, I'm just writing the intermediate steps for clarity. So this is 16 and 4, I think. Okay, so you'll get I think 42, and this is 6.48. Okay, and for triangle inequality, the statement is this, right? So for now, so we have computed the LHS of the inequality. Now we have to check the RHS, which is the sum of the norms. So the sum of the norms is what? Norm of u plus norm of v, which is, we have calculated these two norms before, both are 4, so it is 8. And clearly, you know, the inequality, the triangle inequality, is satisfied in this case. So triangle inequality also holds. Okay, alright, so I mean, there were multiple concepts embedded in this first question. So by the way, is my pace okay? Am I going too slow or am I going too fast? Let me know. I mean, I think most of these concepts are known to you, so it's just a recap of the contents for most of you. So yeah, okay, so let's move on to the next question. Question number 2, you are given two matrices A and B, and we have to find the matrix multiplication, the product AB and also BA. Okay, okay, so it's a review of, you know, matrix multiplication, very basic operations. So let's do it quickly. Okay, so the first matrix which is given is 1 2 3 4 5 6, simple. And so the size of this matrix, or the order of this matrix, is 2 cross 3. Why? Because there are how many rows? 2 rows, right? These are the 2 rows, right? This is the first row. What should I do it? This whole thing, this is the first row and this is the second row, correct? So therefore number of rows is 2. And what are the columns? This is the first column, this is the second column, this is the third column. Okay, so there are 3 columns. Okay, sorry, so there are 3 columns. So it's a 2 cross 3. 2 denotes the number of rows, 3 denotes the number of columns. That's how the size of a matrix is governed. Okay, I'll just remove this highlights. Okay, And the second matrix is the matrix B, which is given by 7, 8, 9, 10 and 11, 12. So can someone quickly tell me the size of this matrix B? How many rows are there, how many columns are there?
Three cross two.
3 cross 2, exactly, thank you. So this is 3 cross 2 matrix because there are 3 rows, you see. The first row is 7, 8, this with these elements. Second row is the elements 9 and 10. The third row is formed by the elements 11 and 12. So there are 3 rows and there are 2 columns. Okay, so the horizontal lines are the rows and the vertical lines are the columns. Okay, so there are 2 columns here. The first column has the elements 7, 8, 9. Sorry, 7, 9, 11. Sorry. Okay, this first column. This is the first column. This is the first column with entries 7, 9, 11. And this is the second column with the elements 8, 10 and 12. So there are 2 columns. So 3 rows, 2 columns. Therefore 3 cross 2 matrix. Okay. I mean, these are known to you, but still, I just reiterated these things. So okay, so now you have to find A times B first, the matrix multiplication of A and B. So A is this matrix, I'm rewriting, times B is this matrix. Okay, so before I compute the multiplication, is we have to check if this multiplication or if this product is defined or not, if this operation A times B is defined or not. How do we check? So the first matrix is of dimension 2 cross 3. So I'm using the terms dimension, size, order synonymously here. Okay, but it varies depending on the context. But in this case, we are dealing with the size of the matrix. So assume that, yeah, it implies that thing. So, and the size of the matrix B is 3 cross 2. So you see, you have what you have to check. You have to check these two parameters. This one, these 3 here and this 3 here, which is the same as saying you have to check the number of columns of the first matrix and the number of rows of the second matrix and see if they are matching or not, if they are equal or not. They have to be equal for this operation to be valid, to be defined. Okay, if they are not matching, you can't take their product in this order. Okay, so in this case it is matching, therefore yeah, we can take the product. So what is the result of this? Okay, I'll just mention. And what one more thing, what will be the size of the resultant matrix after performing the product? That also you can check. Basically these two are matching, right? This 3 and this 3, these two are matching, therefore you can perform the product and the result will be of size. Basically you discard these two. Okay, and what's remaining is this 2 and 2. So the result will be of size 2 cross 2. This is a way to remember what will be the size of the result. If the first matrix, let's say A, is of size m cross n, and the second matrix is of size, it has to be, the number of rows has to be n for the product to be defined, let's say n cross p, then if it is a matrix, it results in a matrix C, then the C will be of size m cross p. This is what I need to say. Okay, so yeah, so yeah, let me remove this. Okay, yeah, now to compute the product, how do we do that? Okay, so it will be a 2 cross 2 matrix that we know, but how do we do that? So the first, let's say the first entry, okay, let's say the first entry is um, C11. Okay, the second, okay, I think people are joining. Yeah, so this 1 1, this index means first row and first column, the element of first row and first column. So Cij in general means entry of ith row and jth column. Okay, the first index is the row index and the second index is the column index. So this is C11. Okay, let's say, let me call it by C11, the first element belonging to the first row and first column. Similarly, the element in the first row and second column will be C12. The element in the second row and first column would be C21, and the element in the second row and second column would be C22. Okay, let's call them this. So in order to find C11, so the element of first row and first column, what do? You have to take the first row of the first matrix, this row, okay, and you have to take the first column of the second matrix, this column, and perform their inner product. Okay, that will give you C11. So if you take the pointwise product, the inner product of these two vectors, what do you get? It's simply 1 times 7 plus 2 times 9 plus 3 times 11. Correct? So let me quickly write it down. C11 will be 1 times 7 plus 2 times 9 plus 3 times 11. Is everyone clear with this step? How do we compute the first entry of this resultant matrix? I hope it's clear. Okay. Now how do we compute C12? For computing C12, you take, so the first index is 1, right? So you take the first row of matrix A and the second index is 2, so you take the second column of matrix B and take their inner products. It's like this. So it's C12, therefore you do the first row of A with the second column of B. You find that inner product. So that will be 1 times 8 plus 2 times 10 plus 3 times 12. Correct? Okay. So I'm just writing C12. You will get 1 times 8 plus 2 times 10 plus 3 times 12. Great. And similarly, the other terms also you can compute. This will be 4 times 7 plus 5 times 9 plus 6 times 11. Similarly, the last entry would be 4 times 8 plus 5 times 10 plus 6 times 12, I think. Okay. It's a bit messy here. Let me see if I can fit. 5 times 10 plus 6 times 12. Okay. Okay. And of course this is of size 2 cross 2, and so what we get is 58. Sorry for my terrible handwriting again. So this is 58, 64, 139 and 154. This is a 2 cross 2 matrix. Fine. Okay. Now you also have to find B times A, the reverse order. So B times A is what? Let me write the B matrix first. This is 7, 8, 9, 10, 11, 12. Okay. This is 3 cross 2 matrix. And what is matrix A? It is 1, 2, 3, 4, 5, 6. Okay. So this is 2 cross 3. Again, let us check if the product is defined or not. So what do we need to check? The number of columns of the first matrix in the product, which is the number of columns of matrix B here, which is equal to 2. Okay, we have to check it with the number of rows of the next matrix, so which is the number of rows of matrix A. Okay, which is 2. So these two are clearly matching, so we can perform the product. And what will be the result of the product? You just eliminate these two. What you are left with is 3 cross 3. So the size would be 3 cross 3. Okay, great. So yeah, so this will be a 3 cross 3. So let me make it a bit larger. So let's say this. This will be 3 cross 3. Can someone tell me what will be the first entry in the first row and first column? Yeah, feel free to unmute and respond. I mean, there's no right or wrong answer. Just feel free to participate. What will be the first entry of the resultant matrix in the first row and first column? You have to take the inner product of, yeah, go ahead,
39.
39, exactly. Yeah, basically what she's saying is you have to take the inner product of first row of B with the first column of A. So if you take the inner product, it is 7 times 1 plus 8 times 4, which is exactly 39. Good. So okay, so I'll just quickly finish this off. So this is, oops, this is 7 times 1. How do we get 39? This is 7 times 1 plus 8 times 4. And similarly for the element, for the entry 1 comma 2, you will get 7 times 2 plus 8 times 5. For the element 1 comma 3, you will get, okay, okay, yeah, I think all these contents are familiar to most of you, so things might be redundant, might seem redundant today. Okay, so this is, and finally 11 cross 1 plus, okay, And lastly, okay, great. So if you just calculate, you'll get 39, 54, 69, 49, 68, 87, 59, 82, 105. Okay, so this is a 3 cross 3 matrix. So from this result, by observing the result of B times A and the result of A times B, what can you say? These two are different, right? The results are different. In the first case we got a entirely different matrix which is of size 2 cross 2. In the second case we ended up with a matrix of size 3 cross 3. So clearly different. So which means A times B is not the same as B times A. Therefore A times B is not necessarily the same as B times A, or in other words, as you know, matrix multiplication is not commutative. So a similar observation that we made in the first question with respect to inner products of complex vectors, right? Okay. Now let's move on to the third question. Third question is again straightforward. We are given a complex matrix A, which is a 2 cross 3 matrix. We have to find the A transpose and A Hermitian. Very simple. So I won't take long for this because we have already seen these concepts. So the matrix I'm just writing, the matrix A, yeah. So what is A transpose? So to compute the transpose, what you do is you exchange the rows with the columns. In other words, the rows becomes the columns and vice versa. Okay. So if A is of size m cross n, then A transpose is of size n cross m. Okay. So this what it becomes is, see, the first row is this. First row of A is this, right? Now this row will become the first column of A transpose. Okay. So the first column will be 1 minus 2 minus I and 5. Okay. Similarly, this second row of A will become the second column of A transpose. So this is 1 plus I 4 minus 2I. This is your A transpose and the size is 3 cross 2 because now you have 3 rows and 2 columns. Correct? And what is A Hermitian? Hermitian is nothing but the transpose conjugate. You already have taken A transpose, you have already performed the transpose. Now on top of that you have to take the complex conjugate to arrive at A Hermitian. So just take the complex conjugate of A transpose. That will give you 1 minus I minus 2 plus I minus I 5 4 plus 2I. Hope I have written it correctly. So this is again of size 3 cross 2. And so yeah, what is A Hermitian is nothing but the complex conjugate of A, the whole transpose, or you can do it the other way. First take the transpose and then take the complex conjugate. So star denotes the complex conjugate. Okay, great. Okay, now okay, in question number 4 we are asked to convert the following matrix A into its row echelon form, or REF, and also into its reduced row echelon form, RREF. Okay, so does anyone know, like is everyone familiar with the notion of REF and RREF? Can someone tell me what are the conditions uh, required to be satisfied by a matrix to be in its row echelon form?
Uh, it is about pivot elements. It has to be one.
Oh,
And
are you talking about the row echelon form or the reduced row echelon form?
reduced row echelon form.
Correct. For reduced row echelon form, the pivots have to be one, and what else?
And for I think for RREF, other elements have to be zero,
Correct.
and it has one in the next column.
Correct. I
Hello.
get what you're trying to say. Yeah. Anyone else wanted to say something? Okay. Yeah. So thank you. So it's I get your point. You're correct. So there are two forms. So row echelon form and reduced row echelon form. Okay. Row echelon form of a matrix is not unique. Okay, you can perform these steps are known as row operations, okay, or row reduction or Gaussian elimination. There are different terminologies. There are certain allowed row operations which you can perform. I prefer to stick to row operations. Some people might do column operations. I'm not sure about that, but we will stick to row operations. Okay, so there are certain operations which are allowed. On doing that, you end up with a form known as the row echelon form. So what is the row echelon form condition? So if there is any all zero row containing all zeros, if any, then they should lie at the bottom of the matrix. Firstly, that's the first condition. And someone introduced the term pivot. The pivot entry is the first non-zero entry of any row, or the leading non-zero entry of any row. That's called the pivot. Okay, so for example, for this matrix A, the pivot of the first row is 8, because 8 is the first non-zero entry of row 1. Correct? Okay, so these are the two conditions. And yeah, so the second condition, I didn't say it yet. So the second condition says that the pivot of every row is on the right of the leading entry of the pivot of every row above. Okay, so there's a shift as you go downwards. Okay, I'm reiterating it. Pivot of every row is on the right of the pivot of every row above. Okay, this is the condition for row echelon form. And for reduced row echelon form, and mind it that the reduced row echelon form, unlike the row echelon form, is always unique for a matrix. The RREF is always unique. So for a matrix to be in RREF, the conditions are firstly it has to be in row echelon form, it has to be in REF. Okay, that's by default. And on top of that, as someone said it rightly, all the pivots should be one. Strictly they should be one. In row echelon form there can be some non-zero entries, that's fine. I mean, they can be one, they can be two, three, whatever. but for reduced row echelon form it should be 1, and in every column the pivots are the only non-zero entries in reduced row echelon form. Okay, all the other entries are 0 in every pivot column. So these are the conditions. Okay, so it's not very hard to see actually, so let's do a problem on this. Let's do. Should I start here or okay, yeah, I can. So what I'm trying to do is I'm solving them, and on top of that I'm just trying to make some observations or some notes, some points. Okay. Okay, so REF conditions, I'll just maybe quickly write it. REF conditions. REF is row echelon form. First is all the 0 rows, if any, are at the bottom. Secondly, pivot I already defined is the first non-zero entry of any row, the leading non-zero entry. So every row is on the right side, is on the right of the leading entry or pivot of every row above. Okay, these are the two conditions. And for RREF, which is the reduced row echelon form, the conditions are firstly the default. It's a more stronger condition, so it has to be at first in REF, must be in REF. Okay, the row echelon form. Second condition is all the pivots are 1. Third condition is pivots are the only non-zero entries of the basic columns. Okay, fine. So if I have to give you an example, okay, let's say an example of an RDF matrix or a row echelon form matrix is a matrix of this form. Let's say 1, it could be star star star. So star denotes, like, star is like um, can be anything. Okay, so don't care, can be anything. It can be 0 or non-zero. The second row, let's say 0 0 2, and again star star, again 0 0 0 1 star, and let's say all 0 row. Okay, so what are the pivots of this row echelon form? This is the first pivot because that's the first non-zero entry of first row. This is the second pivot because that's the first leading non-zero entry of second row, and similarly this is the third pivot. These are the 3 pivots, correct? And does it satisfy the conditions of REF matrix? Yes, it satisfies. See, the pivot 2 is to the right of this pivot above. Similarly, this pivot 1 is to the right of this pivot 2, and the all 0 row is at the bottom. Okay, so those are the 2 conditions for REF, right? And they are satisfied. And for RREF matrix, if you have to give an example, one very standard example could be the identity matrix. Let's say the 3 cross 3 identity matrix. Correct. See here the pivots are these 1, and that was the condition required for RREF, right? All the pivots should be 1, must be in REF. Of course it is in REF. And also the third condition is, in a column the pivot should be the only non-zero entries. You take all the 3 columns, you see that the pivots which are equal to 1 are the only non-zero entries, rest all are 0. Correct. And another example could be something like this. Let's say 1 0 0 1 0 1 0 3 0 0 1 minus 3 and all 0. Okay, so what are the pivots for this matrix? Can someone tell me, which I just wrote? Can someone help me highlight the pivots for this matrix? So the you take every row and observe the first non-zero entry of that row. That's the pivot of that row. So tell me, for this matrix, what are the pivots? Let's consider the first row. What is the pivot location for the first row? Yeah, feel free to respond. I mean, even if it's not right, it's perfectly fine. Or if the question is not clear to me, let me know. For this matrix, the matrix which I have written here, this matrix, I'm talking about this matrix. I am asking you to identify the pivots. So pivots.
It's one.
Yeah, sorry, someone is saying something. Hello.
It's one.
One.
Position.
Yeah, exactly. So this one, right? Not this one. The one on the right, not that one, because this one is the first that you encountered, first non-zero. You are going from left to right, so correct. So this is one pivot. And for the second row, what is the pivot element?
So one again.
One again. For the third row,
One. Yeah.
okay. And is there any other pivots?
No.
Okay, good. So the first non-zero entry. Okay. Okay, good. So these circled values are the pivots. The pivots are encircled. I'm just making a note so that when you refer to these notes later, you are able to understand. Okay, great. So now coming to our question, the matrix that was given to us is this: 8 3 minus 13 minus 4 minus 2 6 1 5 3. Okay, have I mentioned question number 4 anywhere? Yeah, I mentioned number 4. Okay, so yeah, you have to convert this given matrix A into its row echelon form, which need not be unique, and also you have to convert it to its reduced row echelon form, which has to be unique. Okay, so let's first uh, see the row echelon form. And before that, one thing which I have not mentioned is what are you allowed to perform. So the allowed, these are called elementary row operations. Okay, I mean, due to restricted time, I can't cover everything in details, but okay, you are performing operations on the rows of this matrix. That's why these are row operations. That's straightforward. And uh, so why these are elementary operations? Because actually every row operation that you perform is essentially a matrix multiplication. Okay, let's say you are scaling the second row by a factor of 2, that is you are multiplying all the elements of second row by 2. That is essentially multiplying the actual original matrix with another matrix, and that matrix is called an elementary matrix. Okay, and why is it known as an elementary matrix? Because that is a matrix which is obtained from the identity matrix by performing a single row operation. Okay, so basically let's say if you do the second row getting mapped to 2 times r2, let's say this means I am multiplying the second row, so r2 denotes second row, so I am multiplying second row by 2 and putting the result, storing the result in the second row back. This is indicating that operation. So if I do this, this is essentially actually the elementary matrix is basically, first you draw the identity matrix. Okay, you perform this operation on this identity matrix. So if you do this, then the identity matrix becomes this, scaling the second row by 2. So this matrix is your elementary matrix, and if you call this as some, let's say whatever, E1, so the after performing this row operation r2 changes to 2 times r2 on A, after doing this you will end up in a matrix which is equal to E1 times A. This is what is happening. So all these row operations are essentially matrix multiplication. Okay, let's say if it would have been some instead of 2 it would have been 3, then you have to do this operation on the identity matrix. So instead of these 2 it would have been 3. Okay, that would have been the elementary matrix. Okay, yeah, so these are, I mean, just aside. Okay, you need not worry too much about these things. Okay, good. So what are the allowed elementary operations? First one, simple one, is row swap. Row swap. Okay, as the name suggests, it is basically you are allowed to exchange any two rows. Number two is scalar multiplication, which I just showed a few minutes ago. R2 changes to 2 times R2. Yeah, you are basically multiplying the second row by a scalar equal to 2. Multiply any row by a constant. Okay, and third one is row summation or addition. Okay, it's like add a you are allowed to add a scalar multiple of one row to another row. Okay, so mathematically, if I had to say, where is the pointer? Okay, so this exchange operation is same as, let's say you are exchanging the ith row and the jth row. So notation wise, this means this Ri getting swapped with Rj, ith row and jth row getting extended. Multiply any row by a constant. So this mathematically means, let's say Ri maps to, or you are multiplying Ri by some alpha times Ri and storing the result in the ith row itself. Okay, and the third one says add a multiple of one row to another row. So let's say you're doing this. So you're multiplying jth row by beta by some scalar and adding the result to the ith row. Okay, the entire result is stored in the ith row. So these are the three elementary row operations that you can perform. Now coming to our questions, I'll just rewrite the matrix A, which is this 1 5 3. We have to convert this into REF as well as RREF. Okay, so what's the first thing that we can do? As you remember, like the pivots, as you go downwards, the pivots should move to the right, correct? So for that reason, um, I find this step, you know, valid, like I mean logical, that consider this entry, this 4. Okay, which should I use? Okay, yeah. So this 4 minus 4. Okay, this entry, my first target can be to make this entry 0 0, correct? Because in that, by making that 0, I can guarantee that the pivot of the second row is located to the right of the pivot of the first row, which is one of the conditions to be satisfied, right? So what is the row operation? Can someone tell me that I need to perform in order to make this element 0? And also sometimes, here, just to make things quick, I will maybe combine these row operations in one step, although that is not very encouraged, but sometimes I will maybe combine scalar multiplication and row summation together. Okay, it's just like a step jumping, but yeah, I mean you can do it in two steps or one step directly. So yeah, how can I make this element 0, this minus 4? One,
So,
huh,
so it could be R1 plus 2 R2.
R1 plus 2 R2, and I have to store that result in R2, right?
R2,
Correct,
yes.
exactly, exactly. So what she said is R2 maps to 2 times R2 plus R1. So this means I am performing this operation and storing it in the second row. Okay, okay. So if I do that, what will I get? I will end up with a matrix which looks like I am not touching the first row, I am not touching the third row, so they will remain as it is. My second row will now get changed after I do this addition and scalar multiplication. So multiply second row by 2 and add it to the first row and store the result in the second row. So what do I get? So minus 4 times 2 is minus 8 plus first row's first element is 8, so minus 8 plus 8 is 0, so this is 0. Again minus 2 times 2 is minus 4 plus 3 is minus 1, so this is minus 1. Similarly 2 times 6 plus minus 30 is again minus 1. Is everyone clear with this step so far? Please unmute if you have any doubts. Okay, now similarly uh, my second strategy could be to make this element, which is 1, make this element 0, because now what I want, now I want the pivot on the third row to be on the right of the pivot on the second row, or else if somehow I can find an all zero row, that should lie at the bottom of this matrix, which is the third row. So for that, one strategy could be to follow again the same along the same direction and try to make this entry 0. So for that, similarly, what can be a suitable row operation? So as we did before, we can also now do, let me change the color, we can do R3 changes to 8 times R3 minus R1. So you see I am combining basically row sum and scalar multiplication together in one step, which, as I said, I mean I'm doing here for quick operation, but it's not encouraged. You can maybe do first R3 changes to 8 times R3, then you do the subtraction on the next row operation, okay? But yeah, I mean you'll end up in the same result. Okay, what happens if you do this? Can someone tell me the result of this? Okay, wait. So what will be the result of this operation? R3 is changing, so R1 and R2 will remain the same.
Sir, it is 0, 37, 37.
Yeah, exactly. So this is 0, 37, 37. Okay, great. So now you observe one thing. Do you find any similarity between the second row and the third row? Do you find any similarity between the second row and the third row? Are these two rows, which are essentially vectors, somehow related? You see some similarity between their structures? Second row is the vector 0, minus 1, minus 1. Third row is the vector 0, 37, 37. So I mean both their first entries are equal to 0, and see, their second entries and third entries are equal. So can't I say that these two rows are actually multiples of each other? The third row is basically minus 37 times the second row. isn't it? So mm, so what I am doing is okay, so what I am saying is, sorry, these two rows or I should say third row is a multiple of the second row, which is R2. Third row is R3. Precisely, R3 is equal to minus 37 times R2. That is clearly visible. So one of the rows is dependent on the other. These two are dependent. So we can easily eliminate the dependency by performing a suitable row operation. And since these two are dependent, one of the dependent rows can be eliminated and transformed into an all zero row using this row operation. That's why it's called reduced row operation. Okay, you are reducing, you are simplifying it, and as you do it in matrix algebra, the solution the solution to the system of linear equations doesn't change. Okay, now so what can I do for this? So therefore okay, let me go. Can I go? Okay, open this. So make the third row vanish, that is 0. Okay, so let me write it here only. So if I do, R3 changes to R3 plus 37 R2. What do I get? The first and second row remains the same. This becomes an all zero row. Correct? Okay. So is this matrix in row echelon form now? Yes. This is in row echelon form. So this is the row echelon form of the matrix A. And this is one possible row echelon form. You can arrive at in some other forms as well by following some different sequence of row operations. Okay, so what are the pivot elements? This is one pivot, this is one pivot. So pivots are encircled. Okay, okay, now let me go to the next page. So REF of A, we just found one possible REF, which is 8 3 minus 13, 0 minus 1 minus 1 and all 0. Okay, so now in order to transform this further into RREF, what can we do? For RREF, the condition states it has to be in REF firstly. We will start from the REF itself. We'll take the REF and then further transform into the RREF. Okay, so it's already in REF. Additionally, what do we need to do? The pivots should be 1. So the pivots are this 8 and minus 1. We have to make them 1. So simply what we can do is we can normalize these two rows. with respective scalars. Okay, so that what one thing we have to do. And also another condition is that for RREF, in every column the pivot should be the only non-zero entry, rest of the entries should be zero. So let me once again circle the pivots. These are the two pivots. So for first column, okay, the other entries are zero other than pivot, fine. For second column, the pivot is -1, so the remaining entries has to be 0. So I want these three to be 0. Make this 0 for RREF, correct? So let's do that first. So how can I do that? If I perform R1 changes to R1 plus 3R2, what do I get? 8. This becomes 0 now. This becomes -16. The second and third row remain the same. Okay, so these are the pivots. Now what's remaining is to convert these pivots into 1, which is straightforward. We can simply normalize the rows. So the first normalization factor would be, for first row would be dividing by 8, and for the second row we have to just multiply with -1. So what we will get is this and this. Okay, so now you see the pivots are strictly 1, and these are the only two pivots. And in every column the entries other than the pivots are 0. So the first column and the second column are the only columns containing the pivots, and the every other entries are 0, okay, other than the pivot. So this is your RREF, row reduced echelon form of F. Okay, great. Now we'll move to the fifth question. Okay, now that we have done the basics, we can little bit increase the pace. Okay, are people with me so far? Okay, yeah. Let's see question number 5. We have to check if these three vectors, they are three-dimensional real vectors. We have to check whether these vectors are linearly independent or linearly dependent. Okay, so recalling your lectures, can someone tell me what is the definition of linear independence of vectors? When do we say that vectors are linearly independent? You can tell me the mathematical formulation as well, like the condition. Let's say there are two vectors, there could be n number of vectors in general. What is the condition uh, for which those two vectors or those n number of vectors to be linearly independent? Can someone tell me quickly? I mean, in words only you can tell me. Okay, are people familiar with the concept of linear independence? I think it was taught in the lectures, right? if I'm not wrong. Yes, can you hear me? Hello. um Hello. Can someone respond? I'm not able to
Sorry.
understand if yeah.
Sorry.
Yeah, so I mean, what I'm asking is like, are people familiar with the concept of linear independence? If yes, then I think someone can quickly tell me. I mean, I think it was covered in the lectures, if I'm not wrong. Okay, anyway, so the thing is like, if there are some n number of vectors, they are said to be linearly independent if the only linear combination of the vectors that equates to 0, the 0 vector, is the all 0 trivial combination. Okay, the only possible combination of the weights is all 0, that will lead to the all 0 vector. Okay, if we can find one of the coefficient to be non-zero, okay, at least one of them non-zero, then we will say that that leads to a linear combination that is equal to 0 vector. Then we will say that the vectors are linearly independent, sorry, linearly dependent. Okay, otherwise, if the only linear combination that gives me 0 is the trivial all 0 combination, then they are linearly independent. Okay, I'm pretty much sure this is covered in the lectures. So linear independence or dependence of vectors. So what we are given is a set of 3 vectors. First one is this, second one is this. By the way, I think your first week's assignment is due. um, I don't know the deadline, I think it's 7th August or something, I think. Yeah, hopefully the questions are straightforward to you. So if there are any doubts in assignment, anything, if you feel there is any mistake or anything not clear, you can, I think there is a discussion forum also in the course web page, so you can post your queries over there also. Okay, and all these notes and everything will be recorded. So I'll upload this in my YouTube channel in a playlist. I'll make a playlist and upload for every week, and this handwritten notes and questions will be, I think, available in the course web page. I think they will create one section called problem solving sessions and so on. So I think all these things will be shared to you, you need not worry. Okay, so these 3 vectors you have to check. So let's take 3 coefficients, 3 scalars, x1, x2, x3. Let's form a linear combination of these 3 vectors like this: x1 times the first vector, x2 times the second vector, plus x3 times the third vector, and I equate this to 0. Okay, this is bold 0. Okay, it's the 0 vector or the null vector. It's basically the 3 cross 1 all 0 column vector. Okay, if this is the condition, we have to find out for what values of x1, x2, x3 this holds true. And if it turns out that the only possible case is x1 equals to x2 equals to x3 equals to 0, all of them are 0, then we will say that these three vectors 8 minus 4 1 3 minus 2 5 and minus 13 6 3 are linearly independent, otherwise they are linearly dependent. Okay, so I can also rewrite this as this. This is on the right hand side, I have the all zero vector, correct? So these are my three system of linear equations. You see there are three unknowns and three equations. Okay, and also we typically can represent this in a matrix form as well. So I can form a matrix with the coefficients of this x1 x2 x3, okay, like this. So this is referred to as the coefficient matrix, and you'll have a variable, a vector of variables, the unknowns, like this, and on the right hand side you have the all zero vector. Okay, let me call this as some matrix A, which is a coefficient matrix. Okay, this is some, let me call this as some vector x, and let me call this as some vector b. Okay, and this is, since the vector b, the constant vector, this is sometimes also known as the constant vector. In this case it is all zero, so this, whenever it is all zero, it is said to be in homogeneous form. Okay, I mean in ax equals to 0, this form. In general, this, in the right hand side it could be some constant vector instead of all 0, some ax equals to b form. Okay, great. So far is it clear how I have written the things? Okay, I'll take that as a yes. So now you see, what you need to do is, as I said, on doing row reduction or this row elementary row operations, this method is known as Gaussian elimination. The solution to the system of these three linear equations, the solution does not change. What you usually do is you form an augmented matrix, the augmented matrix. Okay, what is an augmented matrix? You take this coefficient matrix A and you also add the, I mean not add, I mean you append this constant vector to the right of that coefficient matrix. So basically you form a larger matrix like this. Okay, so in this case what will it be, what will it look like? You write down A, the matrix A, which is this 1 5 3, and you are also appending this vector B, the constant vector, which in our case is the all zero vector. So this is a 3 cross 4 matrix now, the augmented matrix. Now your task is to, from here, your task is to convert to the row echelon form or the reduced row echelon form. I mean converting till the row echelon form is enough. Why you are converting? Because you want to simplify. See, these are essentially the three set of equations, right? 8x1 plus 3x2 minus 13x3 equals to 0. Similarly, minus 4x1 and so on. These are the three equations in three variables that you want to solve. But solving it isn't straightforward. For that, what we are doing is we are doing this row reduction using Gaussian elimination to simplify it in a much more simplified form, which is easier to solve. And what I am saying is this elementary row operation does not change the solution of the system of equations, and that is also easy to follow, because what we are doing here, you see, you are taking the augmented matrix. So it's not that you are just um, so as you are doing the row operations on this coefficient matrix, you are also doing the same thing on the constant vector as well. Okay, so everything is equally modified in that sense. Okay, so that's why the solution remains the same. And we know that we are the subject that we are dealing with is linear algebra, so linearity is holding everywhere. So by linearity, the solution to the system of linear equations does not change as we perform elementary row operations. Great. Now converting this to RREF. Okay, since on the right hand side we already have a all zero vector, I mean regardless of whatever row operations we perform using these three zeros, it always will remain the three zeros, right? Whether you perform R2 changes to 5, R2, R2 changes to R1 plus R3 plus R2, whatever, it's all zero, so it will remain all zero, it doesn't change. All you need to look is this matrix here, 3 cross 3 matrix here, coefficient matrix. So just in the previous question itself, we have converted this matrix. It was the same matrix, 8 3 minus 3 minus 4 minus 2 6 1 5 3. We have converted this into its RREF. You see, this was the RREF, and the RREF is always unique. That's the most, I mean, simplified form. So I will directly write it in its RREF. So that's why I have chosen this. So what you will get is 0 1 1 0 0 0. Okay, this is the RREF. So how we have done is see previous problem. Okay, we have already converted it in RREF. Okay, great. And okay, of course these are the pivots. Now what does my system of equations reduce to? What is my modified system of equations now? It is, so these 1 0 2 sorry 1 0 minus 2, you take the compare the first row. So these entries are the coefficients of x1 x2 and x3 respectively, and the entries of this constant vector on the right is equal to the value which is on the right hand side. So what are the three system of equations now? It is, so the system of linear equations now reduces to, so 1 times x1 plus 0 times x2 minus 2 times x3 equal to 0. So this is from the first row. Okay, from the first row. And similarly from the second row, what can I, okay, yeah, from the second row, 0 times x1 plus 1 times x2 plus 1 times x3 equal to 0. And from the third row, it doesn't give you anything new, it's all 0 equal to 0, so it's 0 equals to 0. It doesn't give you any new information. So this is my system of equations. So what are the, again, what will I, what can I write here? Okay, this is x2 plus x3 x3 equals to 0, and the first one was x1 minus 2x3 equals to 0. So you see now it's much more simplified. It's much more simplified than before. But now here, as you can clearly see, we have two equations and there are two variables. Sorry, there are three variables, x1, x2, x3. So one of them can be treated as a free variable. Okay, so here the free variable can be x3, and there is a way to decide your free variable as well. So what are the pivots here? So this one and this one, these are the pivots, right? So which means that the uh, pivot columns are the first and second column in which the pivots are present. Correct? The column in which the pivot is not present is the third column. So third. So therefore the third variable is your free variable. That's usually how you decide the three variable. Okay? So choose x3 as the free variable, and usually the variables which correspond to the pivot columns, in this case x1 and x2, because those are the first two pivot columns, are known as basic variables, but I'm not going into the details. So if you choose x3 as the free variable, what do you get? Okay, firstly from this one, what do you get? You get x2 equals to minus x3, and from this equation you get x1 equals to 2x3. So you see that x1 and x2 both can be expressed in terms of x3. So x3 is the free variable here. So the solution is of the form 2x3 comma minus x3 comma x3. You can simply pull out x3 common, x3 times 2 minus 1 1. Okay, x3 is the free variable. If we choose on choosing, the simplest value which we can choose is x3, let's say 1, we get x1 equals to 2, x2 equals to minus 1, x3 equals to 1. This is one non-trivial combination of weights. Okay, all these are non-zero values, so that their linear combination give you 0. So therefore what is the conclusion? This set of vectors are what? Linearly independent or dependent? We arrived at a possible linear combination with weights which are non-zero. Not all of them are 0. So what does that mean? It means they are linearly dependent, right? And it is easy to check. x1 times the first vector, which means 2 times the first vector, plus x2 times the second vector, minus 1 times the second vector, plus x3 times the third vector, which is plus 1 times the third vector, is indeed the all zero vector. Okay, So therefore the vectors are linearly dependent. x3 was our free variable. If you would have chosen x3 equals to 0, automatically x1 and x2 also would have been 0, but that's just one case. We can get some non-trivial combinations as well, depending on the choice of x3. So the vectors are linearly dependent. So is this clear to everyone? Okay, I see a thumbs up reaction. Maybe if someone has reacted before, sorry, I might have missed, but yeah, you are encouraged to uh, unmute and respond. That way it's better for me to follow actually, otherwise I might miss out. Yeah, thanks. Okay, thanks. So this one is also done. Now the question number 6, and question number 6 is very easy. You see, it's again on linearly dependent and independent vectors. So you are given 4 vectors, u1 u2 v1 v2. First you have to determine if u1 u2, this set forms a linearly dependent set of vectors or an independent set of vectors. Can someone quickly tell me, just by looking at the vectors u1 and u2, whether they are linearly dependent or independent? We are looking at question number 6. Dependent, right? Exactly. Why do you say so? They are dependent. I mean, it's straightforward. Yeah. So I mean, clearly you see that u2 is nothing but 2 times u1. Okay. So they are scalar multiples of each other, or in other words, you can say u1 is half times u2, whatever. So one of them is dependent on the other one. Clearly, there is a dependency relation, right? u2 is 2 times u1, or in other words, um, 2 times u1 minus u2. That's a non-zero non-trivial linear combination that gives you 0. So therefore clearly this is a linearly dependent set. Okay, so whenever you have two vectors, you need not do any calculation. You can simply check if you are able to express one of the vectors as a scalar multiple of the other. If you are able to express, then clearly they are linearly dependent, or else they are linearly independent. So this is a special case. And what about v1 v2? Are they linearly dependent or independent? v1 and v2,
They are independent.
they are independent. Yeah, because there is no way you can express one of them as a multiple of the other. And mathematically also, if you do some alpha 1 v1 plus alpha 2 v2 equated to 0, the only combination of alpha 1 and alpha 2 that will guarantee that is the all 0 case. Both has to be 0. Okay, so yeah, so yeah, that is the thing. Okay, so I hope it is straightforward. So question number 6, u1 uh, u2. So the observation was that u2 is simply 2 times u1, or you can also write u1 equals to half times u. So from this you can write 2 times u1 minus u2 equals to 0. So it's a linearly dependent set because there is a non-trivial combination that gives you the 0 vector. So u1 u2 is a linearly dependent set. Okay, and for the other set v1 and v2, clearly, I mean, here v2 cannot be expressed as a scalar multiplication of, not multiplication, multiple, as a scalar multiple of v1 and vice versa. Therefore v1 v2 forms a linearly independent set. Okay, great. Now moving to the, okay, we'll solve them quickly. So we have to find the inverse of this matrix A, 3 cross 3 matrix in question number 7. Now there are several methods in which you can compute the inverse of a matrix, provided that it is invertible. Okay, one approach could be computing the adjoint of A divided by the determinant of A. Okay, that's I mean, a calculation based approach, and the other way could be doing these elementary row operations, what we have seen so far. Okay, and I think it's better to stick to that approach, and also it makes sense because we have covered the concept in the previous questions. So sometimes it's also known as the Gauss-Jordan method. Okay, again what we do is form an augmented matrix. In this case we augment this matrix A with the identity matrix of the same size, so it's basically A augmented with I, then do the row operations and arrive at a form which is I augmented with A inverse. Okay, so the whatever matrix you will have on the right hand side will be your A inverse, and that makes sense because the left half of the augmented matrix initially is your matrix A, and towards the end that left half after performing row operation becomes identity. And as I mentioned before, these row operations are nothing but a sequence of matrix multiplication, sequence of elementary matrix multiplication, right? As I gave you example. So you keep on multiplying some matrix, some sequence of matrix uh, with A and arrive at A inverse. So that means that product of sequence of elementary matrix is nothing but A inverse, right? Because A inverse times A will only give you identity. And on the right hand side initially you have the identity, you are performing those sequence of steps only on that identity. So you're multiplying A inverse with identity, which will give you A inverse. So that's why you're converting from A augmented with identity to identity augmented with A inverse, that form. Okay, just by simply performing suitable elementary row operations. If this is not clear, I'm just showing it. So matrix inverse, I'm using the Gauss-Jordan method. Also, elementary, essentially we'll do elementary row operations. And again, sorry for my beautiful handwriting, so if it's not clear, let me know. So this is 302 20 minus 2 and 0 1 1. I think this is the matrix given, is it? Yeah. So as I said, first we form the augmented matrix. Okay, the reason why I am giving you an example of finding the inverse of a matrix, although it's known to you, but still why I'm doing this is, first of all, it will further clarify the concept of this row reduction and all. And also, I think in one of the assignment problems, be it the week 1 assignment or the practice assignment, I think there is a problem related to the inverse of a matrix. I'm not sure. So for that only showing. So first we form the augmented matrix as follows. So A augmented with identity matrix of the same size. So this will be 302 20 minus 2 0 1 1, and the identity, since A is 3 cross 3, we also have to take identity of size 3 cross 3, this. Okay, now using row operations, sequence of elementary row operations, we have to convert this whole thing into some form in which the left half will become identity. So it means it is only possible when those sequence of row operations, which is nothing but a matrix, sequence of matrix multiplications, which is also a matrix, has to be A inverse, right? A inverse multiplied with A inverse acting on A will give you identity. So this A is getting mapped to this I, and on the right hand side initially you already have identity. So A inverse acts on identity, so that will give you A inverse itself. Okay, that's the idea. Okay, okay, great. So now we will do that. We'll try to convert it to I augmented with A inverse form. So first, what we can do, there are multiple ways. It not be unique, but one way could be, what appears to me is that this 2 and minus 2 here. Remember, we have to make this left side, this left half of this augmented matrix, as an identity. Okay, so we can cancel out this 2 and minus 2 if we add them together. So one possible way could be simply doing this R1 changes to R1 plus R2, and you will arrive at 500. And remember, you have to do it for the entire R1. entire first row of this entire augmented matrix on the right half as well. If you don't do that, then it's entirely wrong. Okay, so what does the right half become? R1 changes to R1 plus R2. So this is 1 plus 0, 0 plus 1 is 1, 0 plus 0 is 0. Okay, be very careful about this. Okay, rest is the same, like this. And similarly you can do other sequence of row operations. So what I have done in the first step, I have made this to 0. Okay, now what I can do, I can make this entry 0. I mean, it's just one way. You can follow a different approach as well. So for making this 0, what I chose is R2 changes to 5 times R2 minus 2 times R1. Again, I am combining the two row operations together actually. Okay, so if you do this, you will get 1 1 0. So the second row gets modified. Now it becomes 0 0 minus 1, and similarly you have to do for the right half as well. It will become 2 3 0. You can check it later as well. Okay, if there is any mistake, um, just make sure you are able to figure it out. Okay, now what we can do is, you see, um, in the second row of the left half we have 0 0 minus 10. So it's very similar to the third row of the identity matrix. The third row of the identity matrix is 0 0 1, right? So we can simply bring this second row to the third row. We can exchange the second and third rows. Okay, so we'll do that. Second and third row swap, which gives you 5 0 0 1 1 0. This gives you 0 1 1 0 0 1 0 0 minus 5 minus 2 3 0. I hope it's written rightly. Okay, now again we are almost there, except we have to make this 1 here, make this 0. Correct? In order to make it 0, one possible row operation could be R2 changes to 10 times R2 plus R3. So you'll get this matrix. Sorry. Okay, this is, I mean, just to avoid confusion, this is 10, this is 2 3 and again 10. Okay, this is minus 2 3 0. Great, now we are almost there. The left half has the same structure as that of the identity, except for the non-zero entries. The diagonal should be all 1, right? So we have to just scale the rows, that's it. So make these diagonal entries, make them 1, right? So what should we do? R1 becomes R1 by 5, R2 becomes R2 by 10, R3 becomes 2, R3 becomes R3 by minus 10. So now we are done. Okay, and always do it for the entire matrix. Okay, so yeah, so you see now you arrived at the required form. This is your identity and this has to be your A inverse. Okay, therefore A inverse is 1 by 5 1 by 5 0 minus 1 by 5 3 by 10 1 by 5 minus 3 by 10 and 0. And it's a good exercise to check that indeed A inverse A is equal to identity, which is also equal to A times A inverse. We can check that, we can verify. Okay, great. So we are almost towards the end. Last two questions, I'll go through them quickly. So question number 8, there are two vectors A and B. There are 3 cross 1 vectors. For what value of M are the vectors A and B orthogonal? This also you can calculate mentally and tell me directly. What do we need to do for this? Can someone just respond for question number 8?
We need to multiply and check whether it is coming one. I think.
Multiply, can you briefly elaborate? Multiply in the sense?
The dot product should be one, I think, for orthogonal.
Yeah, the dot product or the inner product, it should be 0.
Yeah.
It should be
Oh,
0.
zero. Sorry. Okay.
Correct. Good. So we have to take the inner product of these two vectors and equate it to 0. So that's the condition for orthogonality of two vectors. Okay, so sometimes like in 3D actually you can actually visualize also that these two will be perpendicular. Okay, for example, a simple example could be the vectors 1 0 and 0 1. They're orthogonal. If you perform their dot product, it's 0 simply. They're perpendicular, right? Clearly perpendicular. In fact, the entire all the three bases 1 0 0 0 1 0 0 0 1 in the three-dimensional vector space, they are mutually perpendicular or orthogonal. Okay, so as someone correctly pointed out, so orthogonality of vectors, first vector is given by this, sorry, 3 minus 4 7. Second vector is given by 2 5 and M. So A and B are orthogonal if their inner product, sometimes it's also called the dot product, as someone said, if their inner product is 0. That is, this is the notation of inner product, 0. Okay, and this is scalar 0, this is not the vector 0. Okay, because the result of an inner product is just a scalar, could be a real number or a complex number. So yeah, you just pointwise multiply. Okay, mathematically you take the transpose, because here essentially you are dealing with real vectors, so transpose is enough. In for the case of complex vectors, you have to take the Hermitian, that is the transpose conjugate. So A transpose B is equal to 0. What does that give you? A transpose is this, B is this. Okay, makes sense because this is 1 cross 3, this is 3 cross 1, so the resultant will be 1 cross 1, which is just a scalar. Okay, so I'm writing here only. So 3 into 1 minus 4 into 5 plus 7 into m equal to 0. This is 7m minus 14 equal to 0, or m equals to 2. This is the value of m for which the vectors a and b are orthogonal. Great. Coming to our last problem for today, which is based on the rank of a matrix. Okay, so if you recall your lectures, what is the rank of a matrix? It is the maximum number of linearly independent columns or rows of a matrix is called the rank of a matrix. So the maximum number of linearly independent columns, which is also the column rank, is equal to the maximum number of linearly independent rows, which is the row rank, and both are equal, which is equal to the rank of the matrix. So the given matrix the given matrix in our question is 1 2 3 2 1 4 3 0 5. Hope I have written it correctly. Yeah. So so maximum number of linearly independent rows, which means, like, again we have to do row reduction, Gaussian elimination, perform elementary row operations, and we have to convert that into row echelon form. And in row echelon form, the surviving non-zero rows will be our number of maximum linearly independent rows, which will be equal to the rank of the matrix. Okay, so let's do that. So what we will do is, because the dependent ones will get cancelled, right, they can be eliminated using row operations, and they will become the all zero rows if there are any dependent rows. So let's check that. So we will convert a into its REF, row echelon form. By the way, when I have introduced the REF terminology, where did I introduce it? Okay, let me, for completeness, REF is row echelon form. RREF is reduced row echelon form. Okay, great. Yeah, so we will convert into its REF. So first step could be make this entry 0, correct? Same, the pivot has to be on the right side as we go down. So we can do R2 changes to R2 minus 2R1. So what happens to the second row? First and third row remains unchanged. Second row becomes 0 minus 3 minus 2. Okay, Now what do we have? So again the next step would be to eliminate this guy, this 3, make this 0. Okay, for that what we can do is R3 changes to R3 minus 2 R1, correct? Sorry, R3 changes to R3 minus 3 R1, because we have to eliminate it, make it 0. So the coefficient we need is 3, right? Then only it will become 0. So undoing this, we get 0 minus 6 minus 4. Now what is the observation again? Observe these two rows, the second and the third row. These two rows are scalar multiples of each other. Or in other words, they are dependent. So what we can do is we can eliminate this dependency by eliminating one of them. Therefore eliminate one of them, because from the definition of rank we need to find the maximum number of linearly independent rows. So we have to eliminate the dependent rows if any. So eliminate one of them. So how can we eliminate? See, the third row is basically 2 times the second row, right? So in order to undo that, we can perform this operation. R3 changes to R3 minus 2 R2, and we will end up with 1 2 3 0 minus 3 minus 2, and the third row will become the all 0 row. Okay, so the pivots are basically these two. Okay, 2 pivots, and actually the number of pivots also dictate the rank of the matrix. In this case there are 2 pivots, so the rank will be 2. And the third row here, I didn't want to use this color. Yeah, this is an all 0 row. Okay, so the surviving non-zero rows are the first and second rows, correct? And this indeed is the REF form, row echelon form. This is in the REF form. This is the row echelon form of the matrix. So number of non-zero rows in this row echelon form, how many non-zero rows are there? 2 non-zero rows, and which is also equal to the number of pivots in REF of A is the same as the rank of A. So rank of A is 2. Okay, so with this we have arrived at the end of today's session. I think I took longer than I expected. I hope the session was okay. People were able to follow. Mostly these concepts are a review of what already you are familiar with. So if there are any questions, you can ask, or else we can sign off for today. and we'll meet again on next Friday 6 p.m. Okay then, if there are no questions, I'll stop the recording. Thanks for joining the session, everyone.